In this problem, in continuation with the previous video, instead of a thin rod, they gave you a semicircle. It is a semicircular ring released from the position shown. Released from the position shown. Semicircular ring of mass m, radius r, released from rest in the position shown, resting on a horizontal rough surface. Find mu minimum, minimum value of coefficient of static friction, which is necessary to prevent any slipping of the ring initially. Minimum mu required to prevent slipping when released. Minimum value of mu required to prevent slipping when released initially, in the initial position when released. At that instant it should prevent slipping. Now if you people observe, this is based on the same concept as that of the previous problem which was uploaded. So I actually expect you people to attempt the problem. You, while going through this video, please pause the video and attempt the problem on your own. You will have to use a concept which we derived in center of mass. Center of mass of the semicircular ring. For a thin rod, you took it as L by 2. You took mg acting at L by 2. For a semicircular ring, it is not at R. It is not here. This is not the center of mass of the semicircular ring. I hope you are able to recollect. Now this, when released, it will tend to fall this way. That means center of mass has an acceleration this way and vertically downwards. So here friction will act in the backward direction. Pause the video here, I repeat, and attempt the problem on your own. After you finish the attempt, go through the solution. This will be the center of mass, this will be mg, this will be the normal force. This angle you take it as theta, this distance will be 2r by pi. You will find something interesting here when you calculate the moment of inertia. Right? First of all, let me tell you the dynamic equations. I'll rub this part of the board because I'll need that part of the board. M is the mass of the ring, R is the radius of the ring. You are asked to calculate minimum mu to prevent slipping when released from the position shown. So prevent slipping at the initial instance. Right? My first translational dynamic equation is mg minus n is m into ay. Second, friction is mu n is equal to m into ax. My first equation, second equation. Just as we dealt with in the thin rod, about which point would you prefer to take the torque? Torque should be about the point of contact P. I'll take torque about point P. Advantage, normal force and friction, two forces are passing through the point, and I am eligible to take the torque about point P because the point P is not accelerating. Right? So mg into this perpendicular distance, mg into 2r by pi is I into alpha. This is a tricky part. Find the value of I about A. Now, incidentally, even if you commit a mistake, by chance you will get the correct answer. What do you mean by this? Some students will write I about A is I about O plus M into R square. I about O, they say MR square plus MR square. they get 2 mr square. Incidentally, it is the correct answer, but wrong procedure. This is not the center of mass of the body. Incidentally, it is the correct answer, but wrong procedure. You got it by chance. And why are you getting it by chance? If you analyze carefully, observe this. I about point P is I about C plus M into this distance square. What is this distance square? This distance is R. This distance is 2R by pi. Right? MD square. D square is R square plus 2R by pi whole square. I about P is I about C plus M into D square. This distance D square is R square plus 2R by pi whole square. I used Pythagoras theorem. Not a big deal. Now, I about C, how will you calculate? This procedure I already told you is wrong. Then I about O is I about C plus M into 2R by pi whole square. I about O is I about C plus M into 2R by pi whole square. Parallel access theorem. This I know I about O. How do you know that here? In moment of inertia, as I taught you people, one piece of a pizza, a circular disc, one piece of the circular disc will be mr square by 2. So this will be mr square. This is IC plus M into 2R by pi whole square. Now IC from here I will substitute here. IC from here I will substitute here. Will I get I about P? I about P is mr square M into 2R by pi whole square plus this quantity. I am running short of space. Plus this quantity. You can do that simplification. I am sure. IC, if you substitute here, you will get I about P, which will be 2 mr square. You are getting the same answer in this procedure also. Why don't you let us do it here? It is a mere coincidence for a ring that happens, not for all other bodies. If they would have made this a disk, you would have been in trouble. Right? Or any other body, for instance. It's a mere coincidence. Because of Pythagoras theorem. Maybe not even for a ring. But do not opt for that procedure. Go by the right way. I about C plus M into D square. This is D square. R square plus 2R by pi whole square. Find out I about C using your knowledge of I about O. That IC you substitute here, you will get I about P. Why did I call this I about A? This is I about P. This I about P you substitute here. All three dynamic equations I am done with. What are the constraint relations for you? AX and AY. AX and AY. You know what is the value of this. Call this as D. You know what is the value of this. ACM. Wish I had more space. Have a look at this. Right? Now, ACM is R alpha. This is A. So this part of the board is also not visible. I will have to rub the board to tell you the relation between AX and AY. Or I'll draw it here. Have a look. You will be able to deal with this. This will be R alpha. What is this distance? I'll call this D. PC. I'll call this PC. Right? PC alpha. This has an AX component and AY component which I can substitute here. If this is theta, this is theta, this is theta. If this is theta, this is theta, this is theta. Agreed? And you know the value of tan theta. Tan theta is 2R by pi by R. So 2 by pi is tan theta. Now this is R alpha. PC alpha. I am calling this distance as PC. Now this in the horizontal direction, AX will be PC alpha cos theta. AY will be PC alpha sin theta. PC alpha's vertical component is AY, horizontal component is AX. Three equations, three variables. If you simplify for mu from this, you will be getting pi by pi square minus 2. You will be getting pi by pi square minus 2. Minimum value of mu required to prevent the semicircular ring from slipping when released from the position shown.